Okay, good morning, everyone, and welcome to the Field's COVID-19 seminar series. I will hand you over to Jianhong Wu, who will welcome our guest speaker today.
Thank you. So it's my great pleasure and honor to introduce my dear friend and colleague, Professor Ali Asgary. Ali is a founder and a pioneer in the field of emergency management and business continuity. So he actually one the pioneer of having this field firmly established in Canada. And he is now currently the executive director of the Advanced Disaster Emergency and Rapid Dissemination facility and initiative at York University that was funded by Ontario government. And he is leading a number of projects under this national COVID-19 task forces related to the agent-based disseminations in different settings. So Ali, it's your time.
Thank you. Thank you very much, Jianhong and Sarah, for organizing this session. I'm really happy to be with all of you, and also thank you to participants being with us this morning. As mentioned before, the title of this presentation is based on a work that we started in the summer, just before the schools being open, to respond to the question of the impacts of school reopening on the situation, as well as whether we should or shouldn't test or just explore what and how the impacts of testing would be on the situation. So it's basically trying to explain what we did in this case, trying to link two models that we developed for this situation. We started to develop first a simulation to explore the impacts of testing on mitigating the spread of virus in the schools, and also making an AI model based on that simulation to make it faster and more useful in a sense. So this work, of course, is the result of participation of a large group of researchers listed here also, my friend and colleague, Jianhong, Monica from University of Guelph, Michael from York University's Math Department, Zarko from Math Department also, and Mehdi, who is a postdoc with our group. What I'm trying to cover very briefly, I think explained in this slide. We first developed a disease and testing model, COVID testing model, using agent-based simulation. And this is more kind of visual also, where you can see the movements to and from schools. This, of course, the results, which is now available on the cloud for people to use it if they prefer to use this simulation. And then we use this simulation basically by running it on the cloud, AnyLogic cloud, for a large number of runs to create a large data set, and then use machine learning to develop an AI model based on these simulation results, again, to be mounted online as a web app for the users. So that's what I'm going to explain this morning. I think there is a need for some background to the case, which is in part happening right away. If you open newspapers, listen to radios and TVs here and there, you will see discussions around outbreaks in the schools. People are reacting to those what's happening in the schools. And these are just some of those coverage in the media currently in Ontario and in Canada as a whole, that there are issues, of course, there are outbreaks happening. There are reactions to that from staff, school teachers, school boards, etc. And of course, there are a need for continuation of educational services across the country and in other places everywhere, basically. So there are discussions going on, as you can see. And so it makes the issue some sort of relevant to the discussion and exploration of what we can do or what are the options under these conditions that are happening. Now, this is basically the Ontario data for outbreaks in schools that is as recent as yesterday. As you can see, currently we have about 558 schools in Ontario with COVID cases. This is a number of schools with reported case, okay? And then this is about 11.5% of total schools in Ontario. It's quite number, it's quite significant, although it's not necessarily uniform across the province, but you can see that this is quite high percentage if we consider the outbreak. And currently there is one school that is closed because of the outbreak. So this is again just to mention that this is happening, this exists. You can see from the evidence and numbers that are there. Now, there are a lot of discussions about when it comes to school testing. There are debates around this, whether we should or we shouldn't, both in terms of modeling, scientific discussions, as well as in policy and public discourse and discussions. These are some of the examples, again, of what is currently covered on our media in Canada. Some basically trying to support this testing initiative, and some sort of, you can say, not happy with testing, especially regular heavy testing for different, of course, acceptable reasons. But our case or our study is not really focusing on these issues. Our effort is mainly to understand whether or to what extent testing would work if under certain assumptions and conditions and information that we have, to address some of these or to provide some information to this kind of discussions. Now, on the policy guidelines, there are some published by different government agencies in Canada and overseas. This is one, for example, of those early reports, I would say, or guidelines in European Union developed on school testing. In Canada, as I'm sure many of you know, there are also guidelines provided to school boards by provinces, by federal governments on the overall, how to work with the schools and if and how testing should be done at the school level. And there are, of course, as I said, differences in different provinces and also even at local levels into this issue as well. Now, going into some discussions on testing itself, very briefly, obviously, and as you know, there are a lot of challenges when it comes to testing for schools, considering, in fact, that testing is already a problem at large level, meaning in terms of shortages, in terms of waiting times, etc. So considering those issues, there are also particular issues with or challenges with regard to school testing. First of all, there are debates whether it works, because we have to do too many tests to be able to basically detect a small number of people. And also discussions around how these comfortable tests are, especially for kids. I mean, my own example is that my son, who is going to a university overseas, he said I had to test on arrival, but I asked him, are you willing to do another test? He was saying, no, it's not really fun to do this test. So especially at least the current type of test that we are using. And as tests become more comfortable or painless, things might change, obviously, especially with new innovations in testing. And also issues with regard to false negative and false positive cases where, there are some errors and may make situation sometimes more complicated. As well as the false sense of security for those people who test believing that they have tested and they can do whatever they want, and so with more peace of mind, which may not be really what the test is necessarily all about. And logistical challenges, even at the school level, we know that to manage, you already saw the number of schools in Ontario to for example, run this kind of testing at regular level at the schools is a really high level logistical challenge. Both in terms of cost, in terms of arrangement and supply of materials, etc. And also this, if we want to test these many students, obviously there are a lot of pressure on the existing testing capacities, which may not be ideal in some cases, especially when we do not have even enough tests to test our highly needed people. And also the cost. There are figures, numbers, tests are not free. They cost, although we do not pay for it, but there are costs associated with it anyways. In some countries, they do pay. To test a large number of people involves a lot of cost as well. And also waiting times for the results, that is an issue, although recently it has been reduced to, acceptable level, but waiting time of, for example, 1 to 6 days, it may not be ideal and may not even help as much if tests are going to be too long, especially if you do it larger scale at, for example, a school level. And social acceptance of mass testing, there was issues, discussions in our, scholarly articles here and there. Not many people are really in favor of large mass testing either. And some other issues related to, for example, privacy, especially at the school level. When you test and a student become positive and doesn't have to attend the school, then it's possible to have his or her identity identified. So moving forward, there are also benefits and opportunities with testing. First of all, testing, as we generates a lot of data and information about the virus spread overall, and this can be a surveillance and monitoring tool for controlling the disease. This has been discussed a lot, no need to discuss it further, but within also the school level, if these tests are carried out, they provide information about what's happening at the school level. Testing, what we can also say is that although testing is painful, but is less painful from hospitalization and consequences of really widespread disease transmissions to others. And also it reduces, of course, pressures on different stakeholders in terms of mental pressure, particularly with parents and teachers. Once they know that tests are being carried out, for example, they have they easier handle the situation, assuming that this is a preventative measure. And problems with, of course, asymptomatic cases that is particularly relevant to our simulation is an important issue, especially at youth and younger people being suspect of these. And continuity of operation, that is my own area of focus also, you want schools to continue their operations while under these conditions. One tool that you can use to have both basically continue your operation while under pandemic situation is to test and monitor as much as possible. And so it is relevant also to schools. And also finally, as you know, and it has been discussed widely, this helps with co-infection or overlap between influenza and other and COVID. When you test, it helps to make some sort of clear distinction and easier, basically, especially at the school levels. Now, what we are trying to do basically is to first classify what are the options and strategies when it comes to school testing. And these are based on what our observations of different policies here and there. You can classify all these things into regular testing, where you regularly test some people in a school setting or others, or and one-time testing. This is when you just do a one-time test at the beginning of, for example, season or semester. All teachers, all students. This was one of the policies, for example, conducted in some schools and universities at the beginning of fall semester, just to make sure that the students coming to school don't have are not positive. And or another option is testing the students and teachers with symptoms. So meaning that we just test those that show symptoms as we monitor and screen them coming to school, or even at home when they are screened before going to class or before going to school. So it's only for those who show symptoms. Again, here, this is not universal. Some school boards, some provinces, some countries do this, some don't. And of course, one item or policy is not to test at all. When it comes, our focus is, of course, on regular testing, assuming that this might be an option and policy to consider. Then there are varieties of these kind of testing. One option is to full test or fully test everyone in regular basis, meaning that, for example, weekly, daily, whatever your frequency framework is, but you test everybody at the same time for every day, or once every other day, or once a week, etc. And also random testing of some students, in this case, coming to classes every day or some days, once a week, etc. Now, within this, of course, in our simulation, we are focusing on random testing, considering that, first of all, there is probably no need for full testing, and also, of course, very much costly. And one option of random testing is, of course, to test everybody at the same time. Now, within this, there are some methods or options available where we have considered them in our simulation in particular. For example, daily testing, random testing of some students in a daily basis. Every day in the school, some students are going to be tested. Or weekly testing, meaning that in a weekly basis, you test some random students. And it could also, I mean, we say students, but it could involve teachers and staff as well, because they interact and they are within the same pool. Test result time, which means in our case, mostly focusing on when the test becomes available, the results. And this impacts, of course, a lot of things, a lot of outcomes of your the simulation and also your testing. Test expiry days, which is the time that we consider a person who has been already tested does not need to be tested, for 1 day, for 1 week, for 2 weeks, or maybe not at all. This is what we mean. We need to decide, and the system or whoever makes decision needs to decide whether and to what what we should consider as expiry dates for tests. Self-isolation of infected students. This is a method inside this testing policy that when you test a student, and if there is a student positive situation, you isolate the other student at home. This is of course discussed, and believe it or not, this has been subject to a lot of debates, especially in terms of how long the students should be self-isolated at home after, whether positive test or with symptoms. Some people, say 24 hours, some 48 hours, and the 14 days, etc. And also testing of all the students in infected class. This is an option also considered in our simulation, which is basically saying that students who, if there is a positive case student in a class, we should self-isolate all these students in that class for that period that is the policy or whatever the policy it is. So we are developing our simulations to address some of these options overall. Now, this simulation, I should say that initially we started thinking of micro simulation of a school with every movement of potential students, teachers, staff, etc. in that. That model still exists, but to make it more universal and applied to a range of possibilities, we decided to make this model as abstract model so that users, depending on the school size that they have in terms of number of classes and also number of students in each class, they can modify the model so that they can see what are the impacts considering their own situation. So there are fluctuations here, and intentionally we made this model so that it addresses a kind of variety of situations in terms of a school setting. So basically, the model is not very complicated. It is a kind of version of SEIR model, with the difference that we obviously implement testing to our model, so that when tests are being conducted to whatever method you apply the testing. For example, if you do a random daily test of some students, if you test a student, this susceptible student obviously would not become positive, but this is counted as a student who has been tested. And so depending on their next round of testing, this person would remain as tested until the time that the test expires. And same with the exposed. These people, if tested exposed, then again, the outcome would be negative, obviously, but it's counted as someone who has been tested. But we have also infected asymptomatic and pre-symptomatic and infected symptomatics within our model. And in each, these are the cases where, of course, transmission happens, and transmission is based on the parameters that we got from Ontario and Canada-wide parameters setting for these kind of models. And here we have a case where, a situation where a student that is infected is going to be self-isolated, whether by test or by household or school type of a screening. So we allow a rate of students to be self-isolated based on testing. And now this state chart here takes care of the situation in terms of students being at home or at a school. Students who have been tested positive, for example, they would not go to a school till the time frame that they can go back to a school. That is, the average time that we consider for the model. Yeah, I think that is basically the structure of the agent-based model for the disease transmission and interconnection with the testing and the movement between home and school. Now, these are some of the parameters that we are using in the model for the agent-based model, starting with, for example, number of contacts per day, and transmission probabilities of different types, and rates and periods of asymptomatic latent period, etc., as well as the number of infected students. I should say that this is a simulation, so we run the simulation under different values, parameter values, and initial values of some of the base parameters, especially, for example, number of infected students. Most of all, I would say, all these runs that I'm going to show the results for you are running based on a hypothetical situation where we have, for example, 3 asymptomatic students coming to the school, and then we run the model and see what happens. Obviously, you can run this with 1 student being infected, 2, or whatever, depending on the situation, and it actually comes, or you can use what is happening in the community as a base for what number we should put, or we can put here to explore. And then you have class size. As I said, this is variable. You can change it to a higher level and lower level. And number of classes. Of course, we have some upper bound for each of these and lower bound, but number of classes as well. And number of tests per class, test result time, test expiry time, test frequency, etc. 2 things that we have also here included. I didn't mention them, but these are the options that we have added to the model so that it allows cross classroom transmission. The base model is based on the assumptions that is based on most of the existing protocols, meaning that the students in one class are not going to interact with the students in other classes. There's no, meeting rooms or large, gym, etc. So this connection doesn't exist. But if you see that in your setting situation is not, and there are inter-classroom interaction, you can check this. And also there is an option for shutting down the infected classes, which means you run the model, but you really want to make the model so that if there is an infection in one class, you basically close out class as your policy option. So the model is, as I said, available on the cloud. You can run it, and I can actually run it and try to run it here. I believe you can see my screen. And there are a number of models here. Okay, this is the model that is available to everybody on the cloud. I'm going to put this on the chat if I can. Also, so that if people want to try it, the link should be also available on their site. Okay, so this is the model that we are currently having here. This model has been pre-run here, so you can see. I'm going to talk about the result later, but this is how the results are presented after you run the model on without the visualization. And you can add as many different type of experiments as you wish to this base model, and change, of course, all the parameters that are listed here for your own situation. I'm going to run this one quickly so that you can see a little bit of what happens. So this is when the model starts running. In this case, by accident or randomly, 2 students in 2 classes where we had 3 students infected the student. And it happened that in this run, 2 infected students were in these 2 classes. And so the model runs to calculate what happens. This is quite fast, as you can see. And we have you can see it into the and this is the logic that that is behind this. And these are some of the statistics that you can see as the model runs here. But this is for one single run, and that is why we decided basically to create an AI model and version of this. The single run obviously takes some time, but if you want to run this Monte Carlo simulation for example, 500 run to produce the results that are useful for you, it takes, of course, longer. And so to conserve some time and also make it easier for those who are not familiar with this kind of simulation environment, we built the AI version of the model. So I'm going back to the presentation. So now very quickly, I'm going to show you some of the results we got from this simulation-based simulation that, as I showed you before. This is for a regular random daily testing with a different number of tests per day. If, for example, we do no daily test in that school with that kind of parameter setting, we will end up in 60 days. If there are infection in the school, you will end up with this number of infection in the school with, you know, all these protocols that we currently have. Yes.
Jian, to interrupt you. So in the online version that you just sent in, we need to log in to be able to run it.
Okay, I probably I put the wrong link, but I'm going to copy. Thank you for letting me know. I'm going to copy it from the model itself that is here. So this is the model that is public version. I'm gonna. This is, you see, shared with everyone, I think. Yeah, copy link and paste it here. Thank you, and sorry for that. Okay, let me know if this was not working either, but I believe it should because it is available on. So
yeah, it works. Thank you.
Thank you very much. So as you can see here, in this case, if you, for example, do 5 daily tests in each class, you would be able to significantly reduce the transmission. And in fact, this graph is for infected students. You would be able to reduce basically, because as you find those cases, you will be isolating them, and then it will reduce the transmission. And we are able to extract other results from this simulation in terms of, for example, what happens in terms of number of tests that you need to do over time. If you carry out, you know, different types of scenarios or testing strategies that you have, where you can compare and see which one is more effective, which one is possible for you, considering, for example, the testing capacity that you have, or thinking that, you know, what you would need if you want to select a certain strategy. This is another running of the model when you do basically weekly test. This is, for example, 1 test per week in each class on the top. And this is when you do it 25 tests per class per week. This is like the whole class every week. You would be able to reduce, but it's not as much as, for example, a regular daily or, you know, some numbers in a daily basis, because this you know, lag period that you have generates some more infection in between. So this may not be helpful as much. Again, when you do weekly testing, these are the number of tests that you have to do, and these are also the outcome of your test in terms of number of tested students and number of tested isolated students. This is the green one, and number of tested isolated in 60 days and 30 days. How many students will be isolated or basically out of class under this measure. This is the results for same-day test results, because we conduct the same testing, but assuming different test results. So meaning trying to understand if we speed up the testing results, which helps, for example, identifying and isolating suspected cases or positive cases, how long or how much impact that would have in our situation. This is, for example, when you do the same day, and this is when you do 3 days, which is the current buffer in Ontario, for example, between 1 to 3 days. So obviously, the faster you provide the results, the less impact it would have, or in terms of transmission. Here is, you see, the maximum would be like near about 30, and here is, you are talking about 40 or 50. This is an example of the strategy where you home isolate infected class, meaning that if there is a, I mentioned this before, if there is a student in one class with positive results, you decide to self-isolate the whole class. And this is what you see in terms of this yellow shows those or number of students tested and isolated in this scenario, and of course the transmission for, again, we run this simulation for 1 test per day. What would be the impacts when you find and self-isolate the whole class, and when you do 5 tests and self-isolate the whole class? You see, this is like going to up to 10 compared to this one that is close to 15, for example. And again, just same results for this strategy, comparing the situation after for 30 days and 60 days in terms of number of tested students and number of infected students found based on the tests. That's the continuation of the results that I showed you before. Also, the same, another strategy with comparing the results for 30 days versus 60 days of running the model. The reason we do this and allow the model to simulate for different time frame is basically for planning purposes, logistic purposes, when they see that the preparation for testing should be done for a period of time. So this model enables that to happen. Now, if you are interested in learning more about details of these results, this has been under review now, but the preprint of the paper is available online. You can take a look, and also happy to hear your comments and suggestions on that. Now, building on this, as I said before, I'm now going to explain a little bit about the AI model we developed here. I think Zarko is also here in case you have more detailed question about this. Basically, this is a neural network with 5-layer design, fully connected feed-forward architecture used in this model. It's quite large in terms of output parameters, about 1,300. And there are 200 neurons in the final hidden layer that is here. And sorry, going back to here, I just wanted to shift this. This provides enough information for our model to predict reasonably well considering all these large number of parameters and ranges for all types of parameters that we have. Now, inside the model, for this model, we used, of course, the same parameters that we had in the initial model, but here we are to create and generate large samples. We decided to define some ranges for different parameters. Wherever we have distribution, we use distribution, existing distribution. When we didn't, we use uniform distribution or ranges that seem to be meaningful and reasonable based on the studies here and there. But this is the list of parameters and their ranges for our AI data generation and training. Now, the final model that was trained on the simulation, the any logic simulation that I showed you was run for close to 125,000, of course more, but for this, for the purpose of this AI, 100,000 of those samples were used for training and 25,000 for testing. And this shows the model accuracy, which, as you can see, it's about an error of 14.6% overall. And also for each output, you have this amount of error for that. But looking at this as a whole, the model seems to be reasonably be able to predict reasonably well the output variables that we include in the simulation and model. And these are some of the outputs of the random output of putting this random values for our parameters to the AI model that is shown here. We aim to basically turn this model into a web application. This is in process, halfway through, so that people, without having the simulation or going to cloud, they can just put their parameters, what we suggest or what is based on their school settings, and run the model and see what the outcomes would be based on their own parameters. So I think that is basically it. For the sake of time, I'm gonna stop here. And if there are questions, myself, my colleagues here would be happy to answer. Thank you very much for listening and being with us.
Thank you, Ali. Yeah, thank you, Ali. So, for again, on behalf of the Fields Institute and Dr. Kumar Muti, I want to thank you again for coming to present this work. And any questions from the audience? If you can raise your hand, or you can send this by chat. Maybe I can ask the first questions. And what is really the challenge for this to be received by, at least by any of the Canadian government?
I think the challenge is, well, from my side, I think that I stop a bit because my internet shows some signals. From my point, I think the challenge is probably more or less the costs involved of doing the test and the situations. Although there are beliefs that this may not need, schools might not need heavy testing, but the challenge is in part that, and I think as tests becomes more available and probably less costly and easy to use, like what we had initially with mask, you saw in the mask situation at the very beginning, there was lots of discussions whether we should use or shouldn't, and then gradually everything shifted to use and heavy use of mask everywhere. I think testing, although it has more logistical situations and issues, it may become more widely used if technology changes make it easier. That's my opinion based on what I see, but others may have different views on that.
Well, Jacques Bellet is here from Montreal, and we're wondering, since you also quoted the discussions from the newspaper, I'm wondering if any discussions from Montreal side.
You want a question?
I have one question, yes, and your comments.
Can your model account for the different policies that Quebec and Ontario are incorporating? One of the issues comparing provinces is that the Quebec government is very, very keen on doing the utmost to keep the schools open and also the daycare centers. In terms of organization of society, that's a very, very primary goal. How does that appear in your model? Can you change thresholds for school openings and parameter adjustments like that?
I think this is when we build it, this is we aim to make it as universal as possible, at least based on the parameters that we have. But and the question, I think, is about if you certainly want to have the schools open, and that is the policy, then I believe there should be a stronger testing policy associated with that, if that is the overall policy. Considering that it's harder if you want to remain open widely without additional tool. So to respond, I think our model is kind of independent of that. It can be used the same, different policy environment, I believe. And then you can adjust the model based on, particularities of your testing policy, your school sizes, number of tests you want to do, etc.
It would be indeed very interesting to do a comparative study between Quebec and Ontario, in the sense that some of the social distance measures and the reopening timing are different. So this comparative study might really provide some insight about the difference and common features of the epidemic trends in both the trajectories in both provinces. It would be very interesting to do that.
Because the assumption of this model is basically that whoever is going to use this, they want to use it for testing, meaning that they already have decided to test. But what they don't know is how many to test, how frequently to test, these kind of options that are available, and makes them, let's say, their testing policies more efficient, more effective, and less costly. That is about that.
Okay, any other questions, comments?
I have a question.
Yes, Kyoto.
Yeah, okay. Yeah, thank you very much for the interesting talk. Actually, I wonder how the initial infected students in a class affect the result, and are you doing any cost analysis depending on different initial distribution scenarios of infection in a class? like how often you have to do the test?
Yes, a very good question. Thank you, Kiranga. In this model, the transmission, once a student is, once a asymptomatic student comes into the school and going to her or his own class, he's going to or she's going to infect students in that class. Currently, it is based on a random number, based on the assigned contact numbers that we have put in the model. That is in our parameter setting, it is 3.4, I believe. Based on that rate, it's going to randomly infect number of students in that class. However, again, this depending on other factors that you can include in your transmission rate or contact, basically. You can make changes on that, considering, for example, I mean, this is a good idea, in fact, to add to the model and enhance it if you want to make it more complicated in terms of these discussions that we actually had earlier, including, for example, size of the class. So larger classes may have less transmission rates compared to smaller congested classes. And also ventilation and other, environmental factors that we haven't included in the model, but you can indirectly add them through your transmission rate, contact rates, etc.
Yeah, thank you very much. Yeah, I always think that maybe it's probably important to think about external force of infection, because how often you should do is really related with yeah, how many people are there infected, right? So yeah.
Absolutely.
Yeah, thank you very much. Yeah.
Thank you.
Thank you. So just I should note that I just see an invitation from the Public Health Agency of Canada to Ali Asgary for another lecture next Tuesday afternoon for his presentation of similar structural part for mass vaccination. So I don't know if Ali will accept the invitation or not, but otherwise that will be another opportunity to expose to this simulation for another mass strategies is involved in vaccination. So with this, yes, good. So with this, I want to thank Ali and for coming to this talk, and I want to thank you all for coming, and looking forward to see you next week, next Tuesday.
Thank you very much, John Hung and Field Institute, Sarah, and everyone.